Hello everybody, welcome into this video. I'm going to just kick off right where I left the last video, which was in the creation of these additional project systems, which were copied from the ones above it. So I've copied the NACA0009 geometry and mesh as well as the solver for it, and I've pasted them in here, renamed them NACA0012, and I'm going to go ahead now and I'm going to bring in the geometry for the NACA0012 and replace what's existing there at the minute, so we can have a comparison between the two airfoils. Now, to get the geometry for this, I'm just going to do the exact same procedure that I did in video 2 of this series, which go to Airfoil tools and generate to the Airfoil plotter my coordinates onto a CSV file, cut out the coordinates of the CSV file, paste them into a text file, open up Discovery and bring them in there, fill it and region it. Now there's a wee bit of work we'll have to do in Discovery, because obviously in Discovery there is geometry existing at the minute in here. So you could look at, yeah, it could be as handy to do it from scratch, but because I already have the mesh already set up, yeah, I can just use the same mesh for it. Now there is another option, is that I can just bring in geometry here, draw it in here, and take that set and put it right into the mesh or into this geometry, and use the same mesh off a new clean geometry without having to worry about the existing geometry. But I'm not going to do that. I'm going to do it this way here because maybe for no other reason than I'm going to have to make sure that the main size is identical same and all that anyway. So let me click onto geometry and let's delete that out of here. Let's get rid of that for now. We'll also have to pick up a little bit from the last video on an error that was made when I was copying and pasting the NACA0009 postscript onto these mesh parameter descriptions, where I obviously overwrit parts of the name. Aft wall inlet and flow field. Actually, this one I did fix up. I didn't fix up the one for this one just yet for the copy, and that's all right. See here, I've inlet aft, and then I've edge size divisions here. I need to get them fixed up, but that's okay. I'll fix that up after I change my geometry, because I'm going to have to go in and do some maybe adjustments to the mesh anyway, and just to check at least that the mesh has adequately captured the new geometry that I'm going to put in. So the NACA0012 geometry, I'm going to go online here and I'm going to select, let's see what's going on here. Move my log. Let's get rid of that. Let's go straight away into Airfoil tools. Airfoil tools. There's actually a good site there as well. I think it's called Big Airfoil, Big Foil, Big Airfoil, Big Airfoil, Big Airfoil, something similar. Big Foil. There it is. There. Seems to be a pretty good site there as well. That I've been doing a little bit with, especially if you're looking for DWG coordinates of your airfoil, of your chosen airfoil, and that one there, has the full remit as well, not just the NACA series, but you can also put in, say, the likes of the J5034. No, it's not the 5034. Can't mind which one. There's a couple of other airfoils there that I have been doing a little bit of work with, but you can bring up the. Let me go back here again. You can bring up, say, for instance, there's the NACA0012. So you can click on into that, and there's your DAT and DXF files. Now, bearing in mind the DXF file does not bring in a spline or a polyline for that matter. It just brings in a series of dots. So to make it useful, I suppose, and it comes in a meter, I think, by standard. You'll have to scale it and you'll have to connect it anyway in Discovery or in one of the modeling packages. So Airfoil tools is just as good as that, and it does give a little bit of additional functionality, for instance, closing leading edges and so on. And if you are using an NACA series exclusively for your stem racing journey, it gives the 4 and 5 digit generators here, which are hugely helpful sometimes. So I don't want any camber. So if there's no camber, there's no max camber position, and I do want a 12% the chord length for a thickness, and I'm going to put in my maximum number 200 points. I'm going to close up my trailing edge, and I'm going to hit plot. Now it's there, it is there. Right, and send this to the Airfoil plotter. I'm going to choose my chord length. So from MATLAB yesterday, and at MATLAB OneNote, here's where we drew it out. To keep a thickness of 2.25 millimeters using an NACA0012 airfoil, we found that a chord length of 18.75 would be resultant. Why 2.25? Well, 2.25 is the thickness that we use for the NACA0009 airfoil. And to keep like for like, so that when we do a comparison of the two airfoils, their drag coefficient and drag forces, that we could say for this thickness, this is the drag force that we're getting. So clearly we're going to have less of a drag force for this one because we have less of a chord length, we have less surface area for. So we would be expecting to see that, but we also might be able to take in other sorts of information from this, especially when we look at the contours and especially looking at the laminar separation bubbles. Friction should be down, but lots of studies have shown that this NACA0012 airfoil is particularly prone to separation bubbles, laminar separation bubbles, at that Reynolds number. Our Reynolds number is there between 40,000 and 60,000 or so, or certainly under 100,000. And some of them, again, depending on the how the airfoil has been produced, there may be slight differences in the angle of attack. It's not exactly 0 degrees. Some of them laminar separation bubbles may form, but they may not reattach, which you don't want to happen. And you might see there that the drag is actually going up, because the drag force, do not forget, is not just as a function of skin friction. Skin friction should come down, will come down, but the drag force itself might necessarily come down, depending on, in a lot of ways, these laminar separation bubbles, again, notably for this particular airfoil. So 18.75 is what we're looking to run with here. Chord 18.75. Radius, thickness 100. That's all good. Don't need to reverse it because it is symmetric, and we'll plot away at that. Okay, I'm going to take my CSV file of coordinates. I'm going to open up this file. I'm going to copy this whole page, Control C, copy the whole lot of that. And what I'm going to do is I have already opened up this file, which is one there that I had for the 25 chord, right? And we did the NACA0009 airfoil in that. Right? But what I'm going to do, let me just close that off again first, just to show you what I'm going to do. I keep spreadsheets of different chord lengths, and I plot all the different airfoils in for that chord length that I'm looking to test. So, for instance, an 18.75 NACA0009 versus an NACA0012 versus an NACA0012 and so on. For 18.75, I'll keep them all in one file. It's probably could be easier maybe to keep files of the airfoil profile and then do different chord lengths in it. And what probably would be the easiest, most sensible way would be just to keep a 100 mil chord length and scale it up and scale it down. Because once you scale it linearly, your data points should come in as well in the right place. But old habits die hard. I'm going to do it this way. So I'm going to actually copy this 25 chord one. I'm going to click F2 and I'm going to call this an 18.75 chord. So, like, where do you stop? There could be an infinite amount of these files. I'm going to keep it as XLSX, and I'm going to open this one. Now I'm just going to have to copy and paste in again. So there's my 9. Right. I do want to keep my conversion points that I kept. Again, you can look at video 2, I think it was, for that one, what that means. So what I'll do is I'm just going to copy the first, Control C, 3 columns, and I'll overwrite these 3 columns here, just by virtue of the fact there that it will keep my conversions here. So these conversions, again, these are going to 0 my my points. It's going to bring my most upstream data point or coordinate for this file, and it's going to place it firmly on the 0, 0 origin. Let me of course rename this and call this 0012. Okay, I'm going to take these here and copy them, and then Shift, Control, and down. Take the whole lot of them. Control C. I'm going to open up a notepad file. Right, there was the 25 chord of the NACA0009, the last one we had. Alright, and I'm going to just add in another one and we paste that one in. This is for the NACA0012 18.75 cord. So let's save that as and put it into the place. There's a 1.2. There's a 100 cord that I've done already for that one. This is going to be 18.75. Right. So again, it's probably an exercise that I'm going to undertake at some stage in the immediate future, is I'm just going to do away with all these varying cord lengths and just stick with a 100mm cord length and use in Excel perhaps a way to scaling them up and scaling them down, or else just scale them up and down in the geometry of Discovery or Design Model or Space Claim, whichever one that you choose to use. Right, so that's that one done. All right, so that's our 0012 in. Let's keep that open for now. Close that one on down. Take this away out of the road and take that out of the road. Job done. And let's get back into the tier. So in geometry, I'm going to open up geometry, and I want to erase out the 0009 airfoil out of this first. Get it out of the flow field. And what I want to do then is I'm going to put in the 0012 in this place. So again, I'm using Discovery here. I always would have used Space Claim, but I believe Space Claim is being phased out. Over time, things are moving to Discovery, so that's it. You need to roll with it. All right, so here we go. There is our airfoil in here. There's the 0009. What I'm going to do is click away into Design. I'll go to File. I'm going to insert Geometry, and I'm going to take in this 12 18.75 cord, open, and that should have placed it in there, and there it is. So as you can see, our leading edge point, back to B here, our leading edge point is in the right location. Let's see if I can go into that. Oh. Our leading edge point is on the origin at 00. This line here is not the origin. That's the line that I set 1mm back to just give a front profile on the nose. All right. So what we can see here is there's no lines here. We deleted all these out, this curve out here. But let's what we want to do is want to fill in this region, really. All right. So we can say take that region, better just fill it all in. Take that. And take that, and let's fill that. Alright, so now we're back filled. Right, what I want to do now is I want to split this region. I want to take this line here and I want to project that on, and I project that on till what? To that face. Take it off, right, and then I'm going to delete out the inside. So there's that. Alright, so what we've done is we've maintained the wall section here, the inlet section, but what we don't have is I want to split this into here, all right, because this is the amount of cord length we're saving by going to the different airfoil. Okay, I'm just going to hit pause for 1 second. I just have someone coming into the room to me here. 1 second. Okay, false alarm. Sorry about that. If you hear the door slamming there in the background, I'm in the lovely surrounds of the SRC today. It just means that someone's coming in, and I'll go to pause, but I will be back. Right, so yeah, I want to split this domain here itself. So I'm going to click away on into that, and let's hit our split. Now, our split tool, I'm going to use this one here. Now, you could be safer. It is a symmetrical airfoil, which means there that the trailing edge tip, the most aft point of this, should be right smack bang on with where we left this before. But when you close the trailing edge, and because we're dealing with a spline to close this, it mightn't necessarily be the case. If you do click it from the trailing edge here, there's no guarantee that you are actually going to land it straight into that point there. But if you click it here, it will land you fairly well into a good enough spot on your trailing edge. Now, what you could also do, indeed, is just join. Let me just scroll this over. join these two edges and resplit it again. Maybe that's what I'll do just to be safe. So I'm going to go on into repair. I'm going to merge faces. I'm going to click that face and that face. Let's hit a merge. And indeed, let's click that face and that face. Let's hit a merge. And now we're remerged. And we have the one big one. And what we can now do is back into design and let's split the face. Let's click a place there that would make sense to us there, snapped onto that and click, and now we'll have our different sections here again. All right. When you have merged faces and you'll be splitting faces again in Design Model, it's very important to look at your name selections. Let me just open that up. I don't know why I hadn't that opened. So apologies, that's probably annoying at home. It is important there to look at your name selections again, just to make sure that the boundaries came in properly, that they were reassigned. And as you can see here, we've lost the wall. I can see my inlet has stayed inlet, looked to be the whole way around. My outlet has stayed my outlet, but indeed I have lost the wall. Okay, so what I'm going to do is I'm going to select my wall, which is that there, click away here and select caps lock wall. And that's that section there, that's our wall. Let's see 1 second on that. I'm going to take my curve off. I'm actually going to delete that curve, that's better. Didn't like that one. I selected the curve as opposed to the boundary of the flow domain. So I just had deleted that. How did I know? It was the symbol that came up here next to inlet outlet. Now this one here is showing an edge. The other one showed a sketch, which was indicative of the shapes, right? The 4 shapes in it. But so delete out that curve. There's no need for that curve there. All right, or you can remove it from the physics. I think you can right click it and do something similar to that. I just tend to delete them. If it's redundant, get rid of it. There's no point hauling baggage around with you. So that's that. So everything looks good there. All right, so I'm gonna X on out of that, and there's my new geometry. And now my mesh is going to need a little bit of work for a couple of reasons. I obviously want to set my parameter names up properly, match them up, but I'm probably also going to have to reassign the edges to the respective boundaries that are set up. So let's go on into mesh. We'll reread the upstream data, and when this launches up the interface, we'll see how much work there is left to do. It shouldn't be that much work. The most annoying thing about when you do this here is especially when you're dealing with biases, it's determining, is the bias still there? Well, it will still be there, but is it biased, in the right orientation? Clicking onto, it's still starting, apologies. So when you click onto it, for whatever the reason is on my computer, I know a lot of computers like that as well, when you have reversed your bias, it takes the graphic away. So when you're looking at it, you don't know, has the bias been applied to that edge, or has it indeed, reversed the bias as I want it, relative to how I had originally seen it. So here we have problems with our matching. We could fix all the scoping on that, but I'm just going to take that out and I'm going to manually fix this. Right, so down into the mesh, edge sizing. These are all just called our edge sizing. Let's see if we can just manage which are which. Right, so this is definitely my inlet sizing. Sizing number 4 is inlet sizing. I'm going to F2 that and call that inlet sizing 4, or edge sizing. I'm going to call that the inlet. That has 122 divisions on it. I'll keep F2. Let's keep it all in caps. Do all right. Now, what I can do is 2 birds with 1 stone. I'm going to take off the parameters and that. I'm going to drop that. I'm going to put that to like, I don't know, 115. I know I don't have a 115, and I'm going to reparameterize that. I jump into my workbench here and I look at my parameters. I see a 115 edge size and inlet. Okay, so it is there. All right. Did take the name through, which was good. All right, come back into, actually keep the parameters open. come back into this. I'll take my P off, change that again to 120 and put the P back on. Now this one here, what are we looking at here? This one was a 121 as well, which I think was wall sizing, and obviously there's nothing selected there because we deleted it away and then we put it back. So let's select our wall divisions on this one. So I'm going to click away onto the geometry. It was this wall up here. That wall, that wall. Of course I didn't have control clicked when I hit that. That. Apply, 4 edges, number of divisions, hard behavior, no bias. That's grand. So I'm going to F2 that and call that edge sizing hyphen wall. Grand. Okay, so that leaves there that I have my aft and I also have my general field. So 220, and I know that this 180 was my general, so 220 definitely was aft, I'm fairly sure. I'm going to jump back into workbench project and just to double check what I had in my earlier parameter set, the 220 was surely the aft divisions. Keep that C4 parameters open. So 220 was certainly aft. Again, no selection. Aft was that, and that. That did have a bias, I believe. Apply that. So there's our bias factor. And we can see that the bottom, this one here, the bias needs reversed on the bottom and the middle. Alright, so I'm going to reverse bias. I'm going to select that one and select that one. Apply that reverse bias, and the graphic did stay with me this time. That looks good. Right, and then I'm going to click up here, F2, and I'm going to call this one hyphen aft. And then this one here, clearly by process of elimination, is going to be my gen FF flow field. Now I only have one edge, and I believe I should have 7 on this one here. Let's move the. So let's go for it. Edge. Right, I'm just going to select again. Boom. 1, 2, 3, 4, 5, 6, 7. Apply 7 edges. And let's have a wee look. So 1, 2, 3. Then 3 edges on the top need to be reversed because these ones here show the more regular spacings along the bottom and coming into the front here. Let's also just make sure, yeah, that we're hitting the airfoil in nicely there. Okay, so reverse bias, no selection, click onto that, then click 1, Control 2, Control 3, and apply. And of course they disappeared in this one, but we're going to assume that it has reversed. That's it, and make sure that blend to neighbors is no for all of them. Okay. Face meshing, no selection. When we want to do face meshing, geometry for the face meshing is make sure, let's click all 6 parts of the field and apply. Click onto mesh and let's generate, see what we get here. This generally does not take too long and hasn't now. We have a problem here. One more face of map mesh controls, right? So we're missing something in here, and this is generally what happens if you have selected not to, or you've selected to use blended face meshes. Let's see if we can figure that out. This is, let me just look in at the airfoil itself. Alright, looks okay. Face mesh. We have selected quadrilaterals on each one of them. Let's just take another look at our inlet size and blend to neighbors. No. Oh, right, gotcha now. Right, I didn't select my 2 faces here. Right, on my airfoil. I have my 2 inlet faces selected here, I just took it for granted when there was something selected that what was selected was correct, incorrectly. So make sure I've selected now 4 of them, including this one and this one. So what had happened there, the non-mapping came in because it had information on one side, but it didn't know really where it was running to. It knew it had to run to that boundary, but it didn't have a path, you know, a target effectively to that size. So there's 4 edges. Mesh. Okay, let's do it again. Generate. So hopefully this will look a lot more structured and mapped, and indeed it does. Alright, so in this one here, let's see what we got. Okay, we still, oh, no, where's my other view controls down here? Let me X that away. It's my quality, my mission quality down here. I believe. Yeah. Sorry folks, see this use Loom software for the screen capture. Sometimes it leaves it difficult to click on the screen. I suppose I'm doing myself no favors on it here either. That's it. Come on. There we are. Updated answers here by the way as well, and for whatever reason my my mouse scroll is going the opposite way, the way I would normally be used to it. But however, so look, there always is a wee bit of work that we can do in these. We do have a massive change in area from one section of the mesh into the other. I don't really like that, albeit it's not detrimental in this case because the skewness, the stretchiness, the difference is in the direction of the velocity along that flow, but all the same, that looks a wee bit ridiculous. I would like to tidy that up, but certainly by the time we get up here, it becomes less apparent. But again, up there is a region of relatively low interest whenever we compare it to what's happening in and around the airfoil. So that, yeah, as I said in the last one, there is always going to be room to improve, and one of the easiest ways would possibly just to double the amount of meshes or the amount of divisions along the airfoil itself. But however, you know, the GCI from our mesh independent study, when we had the NACA0009 airfoil in here, returned back, you know, very favourable values, even though the apparent order seemed to be rough, you know, a wee bit high for my liking, but it was still excusable. I would have, by improving the mesh here slightly, we might have been able to fix that up a wee bit. Okay, but nevertheless, we're not bad. All right, so we're going to run with that. But there is now the NACA0012 airfoil in there. I'm going to X this out and return back onto the workbench. And I'm going to now look at the parameters for my physics. Alright, so here we go. So that's the parameters of them set up. So I can look at the parameters globally, everything that's attached in, which will be the parameters set for system A, B, C, and D, or any of the individual parameters. So looking at the individual parameters here, I have 009s post-scripted to anything in system A. I have number of divisions. Ooh, that didn't update there. 120 and 120. Oh, maybe it is. It's not even an update the project on that. Let me just double check this. Apologies, everybody. Feel free to fast forward past all this. I should have checked that. The good habit started at the start of the video, but now as I'm trying to plow through these with increased speed, I'm losing a wee bit of accuracy, which is not. There we are. If these have wall size, number of divisions, yeah, it hasn't just followed the name through in the same way. Let me just click that off and click it on just to reassign it. That's more than likely the cause of that. Let's look now, parameters. Yeah, there you are. So that has reassigned it. I'm going to take off the number of divisions, which which is at the very end of them, and that was probably legacy from my copy and paste of the early ones. So there we are, mesh divisions, inlet, aft. Hold on a second here, that should not be inlet, sure it shouldn't. Inlet was 180, let's double check that again. That's the wall, that's the inlet. And just double click these on and off again, just to aft. Gen flow field should come in now. And there it is there, gen flow field, number of divisions. Right, inlet, wall, general flow field, and aft. Number of divisions actually has come in when I've put the parameter on. So there's the 4 sections, and similarly in this one here, mesh divisions aft. I've them named slightly different, but that's all right. And what I'm going to do as well is I'm going to postscript, being more careful this time, the NACA0012 control. Take this here, Control C. So when I look at it in the global table, it'll be more apparent to me which belongs to which. Ground. That's that. Nice. No, not so nice. It's done the same thing here again for me. See the way it has, it's overwritten the whole lot when I pasted it, even though only copied and pasted the NACA0012. So that's odd. Apologies everybody for this. Bear with me please. I'm gonna see if I can overwrite them by doing this, and then just do it the old-fashioned way, delete and type. Right, so let me do it this way now, and take out hyphen NACA0012, enter. Take out number of divisions, hyphen NACA0012, wall, take out number of divisions, hyphen NACA0012, and indeed this one, take out number of divisions, ACA0012. Let's just tidy that. Alright, so now there you are. General flow field, aft, wall, and inlet 4, and then NACA0012. Mesh elements for that, I'm not so much going to worry about that. It's going to be the same across everything. Yeah. Let's close these ones. Now let's look at I'm going to change the parameters as well, because I'm going to have max y plus. I want to specify this one as an NACA0009 in system B4. Drag coefficient is an output, but I'll take off OP output, NACA0009. And this one here as well, NACA0009. Okay, that's B4. So there's only 4 that are sorry, B4. There's only 3 parameters that I'm looking for. I put the drag coefficient, the drag force, and the y plus value. Now in D, which is the equivalent, but for the NACA0012, I'm going to do a similar thing. Max y plus OP, NACA0012, drag coefficient, NACA0012, and drag force, NACA0012. Brilliant. Now, if I look at the global one, which is the one I'm really going to use, right, I can not so much worried about that. Outline properties, take that away. I can see my values in here in the outline, but I like using the table sometimes a wee bit more. Bring this down a wee bit. And we could see up here when we move into kind of the output side of things. There's Y pluses. I'm going to close that Y plus up a wee bit, not awful worried. There's, for instance, drag coefficient for the NACA0009, drag force for the NACA0009, mesh orthogonalities I'm also putting as an output. But there's drag coefficient now for the NACA0012 and the drag force for the NACA0012. So I'll be looking at the value in there against the value in here, the value in there against the value in there. That will tell me which airfoil is performing better. So let's accept if drag force is what I'm using to as a gauge of performance. So very simply now, yeah, I can stay in the parameter set and run it from here. I only have one design point, right? So you can update all design points, and this will update the entire project now. So the entire this global table here is taken in both of them systems and component systems, and it'll calculate it, of course, for down here we'll see it as well. Obviously, it'll calculate it for both airfoils. So what I'll do is I'll hit pause here and grab a quick cup of tea, and this should definitely be done by the time I'm back. So I wouldn't expect it should be too long. So I'll see you in a wee bit. Okay, everybody, back again. That has run out, and we've run into a problem. So I had seen this problem come up a couple of times before, and normally what this is because we have to go into Fluent whenever we have brought in a new mesh and there's upstream data that has changed. So the flow field will be given whenever you run it into Fluent. It'll be given a certain tag, if you like, or a certain reference, and we've changed that. So cells, I think they do be called cell zone tags or cell zone names have changed. So sometimes you need to go in and you need to update them manually without just running that with an update design point out in the parameter table or the design point table. So what I'm going to do is I'm going to just go on ahead into setup here, and I'm going to start this for the NACA0012. Obviously the 0009 is fine. We've been running that. Everything is dead on. And it's good to read down at the console here because it tells you an awful lot of information, obviously, of what's going on, but don't take for granted that it's just text flashing through the screen. Process affinities not being set, they always come up. So much about that. Normally it would be the cell zone. See, these cell zone or cell zone names do not match, and you need to rematch them. So I just want to see what this is bringing up, anything like that. And it's square root area here. Cell zone is not, cell count is not defined, cell count is not defined. Setup contains invalid expressions. Okay, so this is where the problems are. So we could see here we have named expressions in here. One with cell count is given here as being invalid because our solid system flow field, this here is obviously this name does not no longer exist. So in a lot of cases, what we'll do first is you see the in file here, I see recorded mesh operations, recorded mesh and incoming mesh match zone names. We don't have them names there, but the incoming names that we do have is solid sys -1 underscore flow field for this. Right, solid sys -1 is they've been matched up. Inlet was matched inlet, outlet to outlet, wall to wall, and now obviously solid system flow field has been matched to solid system or solid sys -1 underscore flow field. That's been done. However, in the named expression, it's looking for, I don't have to do anything there, is what I'm trying to say to you, but this one here, what it's looking for is solid sys -flow field, which doesn't exist, but sys, I can double click and let me see, might not just, maybe will, I think, yeah, -1 does exist. Okay, refresh. Okay, let's see what we got. Yes, so there we are. So now we've counted our amount of meshes, and that's that fixed. All right, so that's normally what it is whenever we do some changes to the say to the name selections, the geometry of the meshing operation or that, and we're bringing in a new cell zone name, or their new cell zones. The names will update, and we'll lose these references. So yeah, no harm. Maybe let's just do that taking it forward. If we now compare another airfoil to this, which we will, we'll do one more after this. Yeah, it's just maybe something to have a look at. You know, we'll just set it in this part of the workflow, is to open up Fluent, run it in here ourselves, and look, there's no harm in doing the whole lot in here now. Initialization, hybrid initialization, initialize. Just as part of, as I said, the standard workflow. This is just how we'll work it from now on. Just open up Fluent and do it. We're not doing anything else in here. I'm going to keep that up at 1,000 iterations, same as the NACA0009, and let this do its thing. All right, so I'll go back into pause here now, and I'll see you in hopefully not so many more minutes. Okay, back again. Yeah, that calculation is now complete, as you can see. So what we can do now is click OK, go back on out into the workbench, look at our table of parameters, and let's see what values we have. So all the messages have been cleared off. I've done that myself. And we can see here now that the drag coefficient, this is for the NACA0009, is at the 0.0159 that we had before, and the drag coefficient here for the NACA0012 is a higher value at 0.0166. Our drag force, 0.215 really newtons for the 0012 versus the 0009, having a lower drag force at 0.205, which, you know, in a lot of ways might be counterintuitive, in that you'd be thinking that the drag force should naturally be less on the airfoil with the lower surface area, which is the NACA0012. Now, yes, it is thicker, but we have scaled that down, so the thickness has been the same. So the 0009 and the 0012, the two airfoils that we're comparing here, have the same thickness, different profiles, which results in different chord lengths. The 0009 being a longer chord length now than the 12. So that is, as I said, counterintuitive. Maybe that you would think in first principles that for a given frontal area, we should negate any sort of variations in drag due to frontal area, because the left balances the right. The two airfoils are the same, so they should, in principle, cancel each other out. The skin friction itself should be less, and probably is less. In fact, I'm wondering, I think skin friction is something that can be calculated. It is actually something that can be calculated in Fluent. I'll not just do it now, but I may do that for the next airfoil that I bring in. Yeah, so it should be less on that, and it probably is. But probably what is happening here is going to be these other sort of parasitic losses, the likes of the laminar separation bubbles that are forming on the NACA 0012 airfoil. Could be what's causing trouble on this. But there is a pretty good way to maybe validate or get a better insight on what's going on and see is it particular to the 0012 airfoil, and that's to bring in a third airfoil, which is what I'm going to go on ahead and do. So what I'll do nice and quickly here for ourselves is shrink this down. I'm going to repeat the whole process again. And I'm going to bring in a new airfoil. The airfoil I'm going to use is going to be one of the Selig airfoils. It is going to have a 12% thickness relative to chord length dimension. So I'm going to put this on pause just to bring it in. I'm going to do a lot of the groundwork here, just copying and pasting these in. If there's anything that's come up that has been strange, I'll certainly come back and I'll mention it. But I'll tell you actually what I will do. We are coming up on a fairly extensive video on this one. I'm going to make one more video after this one, bringing in the next airfoil, do it all together in one airfoil, move it through a wee bit quicker, and that will finish off our independent 2D airfoil evaluations. So then let me into the next kind of phase, which will be sticking a solid wheel behind the airfoil and see how they react to the wheel. Then what we'll do is we'll pull it into 3D, and we might do one variation there with a transient analysis as well. So thanks very much for tuning into this video, and looking forward to seeing you all back hopefully in the next video. Thank you.